Hi guys, welcome to again to my channel. My name is Malasa, and today I'm gonna be showing you the complete design of punching in 20-story building using CSI SAFE 2020. So in the previous tutorial, I have already shown you the basic principles that we are going to follow while designing of slab against a punching shear failure using spreadsheets and manual calculation. Today I'm gonna be show you the detailed design of punching, and this is the tutorial part 27. And the previous one is that was tutorial part 26. Basically, the previous tutorial were based on the design of punching using a spreadsheet, Excel spreadsheet, uh, with reference to a given provided examples. So now today, let's proceed to the today's tutorials, which is tutorial part 27. We'll be focusing on the design of punching using CSI SAFE software. This is the model that I have already exported from etabs, and we have already seen the design of the slab using the CSI SAFE software. So I have already designed this slab using a strip method and finite element method. So for the detailed designing of the slab, you can go back to the tutorial part 25, and you can see and you can get the detailed information how the flat slab is designed using CSI SAFE. Here today we will see and we will check the effect of punching on flat slab. So if you are a new member of this channel, don't forget to subscribe my channel. And if you subscribe my channel, you will be getting more relevant tutorials that have been already prepared with reference to the designing of this 20-story building. And if you are a member of my channel, also don't hesitate providing me comments and questions with regarding to the designing of any civil engineering projects, so that I will be answering your questions, and I will also reply for your comments as much as possible within a short period of time. So don't forget also just pressing the bell icon so that you will be getting a new notification during the uploading of my videos. If you are also interested in all my videos, just try to share my videos to your friends so that your friends will be receiving more and more relevant tutorials that have been already uploaded, and the video that will be also uploaded easily. So now let's proceed to the today's tutorials, which is tutorial part 27, which will be focusing on the detailed designing of budget. So here, this is the slab that I have already designed. Okay, before proceeding to the detailed punching design, now let me run the model once. CSI SAFE software is designing and analyzing this model. Okay, now the analysis and designing of the slab is completed. So now let me display the punching shear. So to do this, just go to the display menu, then here click the show punching shear design button here. So now the The punching demand to capacity ratio is displayed here, and this column is okay for punching shear, and this one is also okay for punching shear, and this one is okay for punching shear. But this column is okay for punching shear, and this is okay for punching, and this is this one, no, all are just okay for punching. So, but when we come to this column, this column, this column, this, and this one, and these ones are failing in punching shear. So here the demand to capacity ratio of the punching exceeds 1. So the applied punching shear exceeds the capacity of the punching resistance of the concrete. So for those of the slab under the columns exposed with the punching shear ratio greater than 1 must be designed for what? For punching shear. So how can we design this the slab which is located around the those columns which pierces the slabs with the higher punching force. So we need to design this for punching. So which one be the governing one here? 1.01, 1.177, 1.129, and just here I think the maximum ratio is it is 1.06, 1.17, 1.19, 1.129. So this one and this ones are, I think the maximum 1.18 here and 1.09. So we can take the governing columns for punching shear. Okay. So here we have two methods. Just we have two methods. So the first one is just using rebar ties. Rebar ties. And the second one is using ropes. So punching can be designed using rebar or stud rails. Here we can use also stud rails. So we can use two methods for the designing of punching. The first one is using rebar or stud rail, and the second one is using drops, and the third one is by increasing the thickness of the slab. By increasing thickness of the slab. So just there may be the slab that needs rebar or stud rails, or there may be slabs that need drops, or there may be a slab that needs an increment of thickness of the slab. So either we can increase the whole thickness of the slab, or we can use the drops, or we can use the stud rail or rebar. So we can see one by one. So to do this, here we can click here, so we can see the output, the punching output here. Now the column punching check, that is the average effective slab thickness is, it is 209. How it comes? How it comes? This one. Here we have a slab here, and we have a bottom reinforcement here, and here we have the reinforcement in y direction, and this one is the reinforcement in x direction. So this is this one. This is the effective depth D. This one. So D, which is equal to total D, that is 250 minus the diameter of the bar, that is 60. The cover, which is 25, minus the diameter of the bar, which is 60. So it is 209 millimeter. And the effective punching parameter is 6025 millimeter. This parameter is what we call U1, which is the basic or the fundamental. The effective punching parameter is 6025. So this is what it is, the outer punching parameter, which is U out. And the coverage, it is 41 millimeter. And the concrete compressive strength is, it is what? It is 25 megapascal. And the reinforcement ratio is, it is 1.25. This is what? 1.25%, which is the reinforcement ratio. And the section is the section of the slab is this 35,401.9 centimeter square. This is the area of the section, and here we have also the area of the section. So here gamma V2, all those results are provided by CSI SAFE, and here this is the moment. That is the moment along in axis 2, and this is the moment along axis 3, and here this is the shear force, which is 753.82, which is nearly around 754. This is 754 kilonewton. So this is VET. And the unbalanced movement is this one, and the unbalanced movement mu3 is this one. So the maximum design shear stress is 0.9 megapascal. So this is the actual induced stress, which is a small VED. This one is the capital VED. And the concrete shear stress capacity, that means VRD. VRDC, which is equal to what? 0.8 megapascal. So the design shear stress, or the actual applied shear stress, exceeds the maximum shear capacity of the concrete. So the ratio is 1.13. So that is why we have to design the concrete for punching. So we need to provide punching reinforcement in order to increase the extra shear resistance capacity of the concrete. So this can be done either of the three methods. In order to design the slab for punching, so we need to select all the columns that have demanded to capacity punching shear ratio greater than 1. I think we need to select all this, and we need to select all this, and we need to select all this, and here this one, we need to select this one, and we need to select also even this one. So, and go to this button and go down here. We need to revise slab punching check override here. So here punching shear design override option is coming. Now check the punching shear, check the punching shear, that is the program determined, because CSI SAFE will determine it automatically. So here I need to select the program determined option, so that CSI SAFE will check the punching shear. And the location or type of columns, or the location of the punching, it is auto. So here we have different options. If we select interior, it will be using for columns that are located in the interior parts of the slab. And if I select edge one, so just if you click this one, what does H4 mean? What does H2 mean? What does coordinate 3? What does H3? What does H1? What does coordinate 2? What does coordinate 4 mean? So you can see all the designation of the the name provided under this list here. So for coordinate 1, coordinate 2, coordinate 3, and coordinate 4. For example, here, just if I wanted to select edge 3, the column that is located on the upper edge parts of the slab. And if I select edge 4, the columns will be located on the left parts, or on the left edges of the panel or the slab. So just you can select the tooltip, or the location of the column here. So I can select auto, so that CSI SAFE will be selecting the location of the column automatically. And the parameter also, CSI SAFE will calculate also the parameter automatically, or just you can specify the parameter, or just you can specify the support or the load size. Here, for example, if I wanted to specify the parameter, just I can specify the parameter here. This is the parameter that should be specified manually. So here we have for example, here I have a column here. Suppose this is the column, and if it is an internal or an interior column, so we'll have this parameter. So here number 1 maybe this one, number 2 maybe this one, number 3 maybe this one, or number 4 maybe this one. So I need to specify all the coordinates of these numbers, so that the outer parameter will be calculated easily. This one, that is, we need to specify the coordinate, or we need to specify support or load size. Here I need to specify the support or load size here. So for the time being, I can select auto, because CSI SAFE will calculate the parameter, that is the outer effective parameter, automatically. And the effective depth, I can select auto, or I can select the specified thickness. So for the time being, I can select auto. If I want to specify the thickness, just I can write here. But for the time being, I can select the auto, so that CSI SAFE will calculate the effective depth based on the provided reinforcement area along in X and in Y direction. And the opening, if there is an opening, CSI SAFE will automatically consider the location of opening. For example, if I have an opening here, so the calculation or the design of punching will consider the opening of the this slab. Because opening that are located closer to the punching zone will have a significant effect on the design of punching. And the other is the reinforcement allowed. So if I want to allow the reinforcement here, I need to select either of rebar ties, or I need to select the stud rail. So for the time being, let me select rebar ties. So the reinforcement pattern is I can select radial or I can select orthogonal. What does radial mean? Here, suppose this is the column. Here, this is the column. So radial arrangement means here this is the radial arrangement of the reinforcement bar for designing of shear, just like this. So all those are rebar sets or stud rail. Rebar sets or stud rail. So here we can put the stud or rebar ties here. So this arrangement, what you call, it is radial arrangement. And the orthogonal arrangement, the second option is, here just we can see it, that is, sorry, this is the radial arrangement and the second one is orthogonal arrangement. What does orthogonal arrangement mean? Here, suppose we have a column here, then we have the rebar sets, and here we have rebar sets that are arranged orthogonally. So we may have rebar ties here. Here we may have rebar ties here, or we may have stud rail. So it depends on the availability of the material. So this type of arrangement, what you call, it is orthogonal arrangement. This one is orthogonal arrangement. So for rebar ties. And we may have also another option, that is stud rail. So we can design our slab for punching using stud rail. So when we use the stud rail, we can follow an orthogonal pattern or radial pattern, as we have already seen for rebar ties. So for the time being, now let me first check for rebar ties with the arrangements of the arrangements of the pattern is an orthogonal. And here the reinforcement yield strength is what? It is 500 or 400. Now let me use it is 500. And here the reinforcement diameter is 10 and the reinforcement spacing is what? It is 10. What does the reinforcement spacing means? The shear leg, the reinforcements of the leg. The distance between this leg and this leg, what you call it is S. The spacing, which is the radial spacing. And the distance between this and this is the tangential spacing, and the distance between this and this is the tangential spacing, and the distance between this and this, what you call this, radial spacing. So we need to specify the spacing of the rebar ties here in orthogonal direction. That means this S1 here, this is S1 and this is what, S2. Here in this case we need to specify S1. This is S1 because we are selecting the rebar ties with orthogonal arrangement, this one. If I select the rebar ties with radial arrangement, so this will be S2. This is what? This is S2. S2. So we need to specify, we need to check this distance, that is the tangential distance, S tangential. So S tangential must be what? Less than what? 2D. Out of the basic parameter. Out of the basic parameter. And within the outer parameter. And S tangential must be less than 1.5 times D within the basic parameter. That means the distance between these ties and these ties within the basic parameter should not exceed what? 1.5 D. So all those maximum limit of the reinforcement bar spacing must be verified carefully while designing the punching shears. So now rebar ties with radial arrangement. Now let me check first for orthogonal arrangement. Now click OK. Now yes. So run the analysis again. Here the reinforcements, the shear reinforcements are provided at every location of punching. Here, this one. Here, that means 8 sets of rebar with 7 rebar ties of diameter 10 millimeter at a spacing of what? 100 millimeter. What does it mean? Here, this indicated that this one is rebar set. This is rebar one set. And this one is rebar ties. Rebar tie leg. So how many rebar tie leg is required? 7 at every rebar set. At every rebar set. Meaning totally 8 rebar sets are required, and at every set of rebar we need to place 7 legs of shear reinforcement. Meaning, suppose here that is 8 rebar set means 1, just like this. Here we may have column here, we may have column here. So here this is number 1, and this is number 2, and this is number 3, and this is number 4, and this is number 5, and this is number 6, and this is number 7, and this is number 8. So how many number of rebar sets are required here? 8. This one. So how many number of rebar ties legs are required per set? That is 7. Here we have 1, 2, 3, 4, 5, 6, 7. Just like this. So 7 rebar ties at every location. So this one also 7. 7. And here we need to place 7 per sets. Just like this. So this arrangement what we call an orthogonal rebar ties arrangement. And when we come to here, that is 10 rebar sets with 7 rebar tie leg at every sets of reinforcement bar. Meaning here we need to put 10. Meaning here that is we need to add 1 extra here. Just like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 10 rebar ties. And 7 at 7 rebar tie legs at every set of rebar. So this is the interpretation of the CSI SAFE shear reinforcement bar results, which is provided on this line. Just like this. So we can just interpret like this, and we can prepare a working drawing for the punching shear. So here this is regarding to the arrangements of the rebar ties in orthogonal direction. So what about if the rebar ties are designed for radial arrangement? So now let's come back again. So to do this, we can unlock the model again. So just we can select this column and go to here, override here. That is punching override here. So I need to select radial arrangements. Now click OK. Now run the analysis. So the punching area which is located around this column will be designed by rebar ties using radial arrangements. So I'm designing the punching for only this column because I have already selected this one. So go to the display menu here. So show the concrete punching shear design. This one. This is the the outputs of punching using rebar ties in radial pattern. So just right click here, just we can see the output, just like this. Here, this is the average effective slab thickness, that is 209 millimeter, and the effective punching per meter is 6025 millimeter, and the cover is 41 millimeter, and the concrete compressive strength is 25, and just like this, all the data are provided here. So here the punching shear ratio is 1.13. So the punching reinforcement design output is here. It is provided. That is the number of single leg stirrup per set is 10, and the number of rebar sets are 10. So what does it mean? Here the number of single leg stirrups is 10, and typical rebar spacing, I mean the number of rebar ties, rebar sets are 10, just like this. Here, sorry. So first I need to put the number of what? First I need to put the number of rebar sets here, 10. So above the neutral axis here, we have 5, and below we'll have 5. Totally, how many rebar sets are required? It is 10. Because this column it is an interior column. Previously I have already selected the interior column. That is why just the outer effective punching parameter looks like this one. So here I can draw just the axis, and now I can it is 5 here, one is here, and the other is here, and the rest is here. How many? 1, 2, 3, 4, 5. Sorry. Here I have this one, and then this one. So 10, totally 10. Just like this, and like this, and here like this. So this is number 1 set, 2 sets, 3 sets, 4 sets, 5 sets, 6 sets, 7 sets, 8 sets. So 8 sets and 2 additional sets are required. I can put here. That is 9 sets and 10 sets of rebar. And how many strap legs are required at every set? 10. That is 10 rebar sets. Number of single leg strap per sets, which is 10. So 1. So those are shear legs. Shear stirrups. Or stud rails. But I have already designed for rebar ties, not stud rails. So this is, the interpretation of what? The outputs. Okay, when we come back again for stud rail design, let's close this one, this one. So now let me select all the columns here and go to the slab design option. So now let me overwrite again. Here the the reinforcement allowed is I have already shown you the rebar ties. Now let me show you the design of punching user start rail. And here this is 500, and here the reinforcement diameter is 10 and the reinforcement spacing is 10. Now click OK. Now run the analysis again. I am designing punching using start rail in radial in radial arrangement. So go to the display menu here. Show punching sheet design. Here this is the punching sheet design using start rail, because previously I have already set the option using start rail. Here I can just like this. Here I have already select the start rail with radial arrangement. So that is the maximum, and the governing one is what? This one. This one is the governing one. So we can take the critical columns which is exposed to punching shear for the design of the rest punching zones. Here, so here we have the start rail. Start rail is nothing but those are here those are start rail. Here this is the start, and this one is the lower metallic plate on which the start will be welded or placed is what you call rails. So here how many rails are required? 10 number of. Those are number of start sets. Start sets. And this is the number of starts. Number of starts means this one. So at every set of starts, we need to place 10 number of starts in radial arrangement. In radial arrangement. That means just like this. In a radial arrangement. How many sets are required? These are 10. 1, 2, 3, just like this. We can add extra here, we can add extra here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can deduct 2 reverse, star sets. So we can put the start rail around the perimeter just like this. As we have already seen in tutorial part 26, that is the radial arrangements of start rails. Just you can go back and check tutorial part 26. So just delete this one. And orthogonal shear design of start rail. So select the whole column here and go to here and override the punching. So start rail using what? Orthogonal arrangement. Now run the analysis. Now display the punching result. Here, digital result here. Just so here previously when we use the radial arrangements of the start rail for the design of punching, this one was 10. What? 10. That is 10 sets of start rails with 7 studies at every set of start rails. So previously it was 10, 10, but now it becomes what? 10, 7. So for in the case of what? Orthogonal arrangement. So in the case of orthogonal arrangement, the shear reinforcement area will be reduced. And in the case of radial arrangement, shear reinforcement area will be increased. So we can prepare the detailed punching shear drawing, that is the punching shear reinforcement details using an AutoCAD, using both radial and tangential or orthogonal arrangements of the rebar ties or stud rails using an AutoCAD. Just I have already prepared here. Just I have already prepared for the orthogonal, the radial as well as for orthogonal arrangements of the shear ties or stud rail. So this is the orthogonal arrangement here. Just we can see it. This is the orthogonal arrangement. And here, how many sets of rivers are required for the specified color? Now let me select this one here. Now let me select this one. And just overwrite here, punching overwrite here. So I can select river ties because I am designing only this color here. I am designing only this portion. So just using river ties in orthogonal arrangement. Now with the provided data here. Now click OK. Yes. So run the analysis again. So here the results are displayed here. That is 10 number of sets of river with 7 river ties per sets of reinforcement. So here just 10 7, meaning that is 10 with 7 diameter what? 10. Meaning the number of sets of rivers are what? How many river sets are required? 10. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can use an extra 2 sets in order to make symmetric arrangements of shear reinforcements. So we can add an extra 2 sets here. So the number of river ties per sets of reinforcements is what? 7. So 1, 2, 3, 4, 5, 6, 7. So 7 river legs are required at every sets of river. So here we have 7, we have 7, we have 7 legs. So and we have 7, we have 7, we have 7. Totally, how many legs are required? It is around 70. 70 legs are required. And here we need to specify also the spacing. Here we need to specify also the spacing. The spacing, the distance between the first river ties in the face of the column must be, that is 3D up to what? 0.5. This is provided in the code. So just we have already provided a spacing of 10 centimeter. So I can place the river ties at every 10 centimeter. Here the first one is here, the second one, the third one, the fourth one, the fifth one, the sixth one, and the seventh one. So where do we stop placing our river ties? Here we can see it. The distance between this distance, the distance between the outer perimeter and the last reinforcement bar must be less than 1.5t, which is less or equal to 230 times 1.5, which is 320 nearly. So this distance is 300. So 300 is less than 320. It is what? Okay. So here, how can we draw this outer perimeter? So this outer perimeter must be drawn using the effective perimeter obtained from CSI SAFE. Now let me come back to here. Just right click here. This one. This is what? It is the effective punching parameter, which is the outer parameter. This one. This parameter is 6025. So using this parameter, we can calculate what? R route. Here, this is R route. R route. So R route can be calculated using the outer effective perimeter value. This can be calculated using a spreadsheet. So I have already shown you in tutorial part 26. Just you can go back to tutorial part 26 and uh, you can watch the video how a route can be calculated based on the outer effective parameter value. So after calculating a route, we can calculate the location of the last parameter. I mean the last reinforcement bar here, that is, which is less or equal to the distance between the outer perimeter and the location of this last reinforcement bar is it is less than 1.5t. So, and also here we can and the other is, this is the distance. I mean, I think this is all about. So what is left here? This one. The first, the first shear reinforcement bar should be located from uh, starting from 0.3 up to 0.5 d distance from the face of the collar. 150 is less than 156. So now it is okay. So the location of the first stirrups from the face of the collar is as per the provision of the code. Okay, so the other controlling distance which is specified in the code is the distance between the two extreme orthogonally located shear ties, which is on x and y axis. That means the distance between these river ties and these river ties, which is the outlined dimension. This distance must be greater than 2d. So 2d means 2 times the effective depth of the slab, which is 2 times 230, which is 426 millimeter. So this dimension is 1522. It exceeds the limit of the distance between the two extreme shear ties, which is located on the two extreme distance of x and y axis. So this concludes that the arrangements of our river ties are under the within the recommended limits of spacing specified in the code. So the other is okay. So we can just prepare a detailed punching machine reinforcement, but just like this. So this is for the interior column because I have already selected the interior column here. This one I have already selected this one because this is the governing one here. All the rest is, here we have 70 rebar ties here, 70 rebar ties here, and 56 rebar ties, and here 56 rebar ties. So the maximum rebar ties, the number of the maximum rebar ties is recorded at this column. That is why just I am selecting this one, and this is for the rebar ties in orthogonal arrangements. So this is for for the interior column. And if our column is the edge column, so we can prepare just like this. Here we have 7 because this one is the governing one, so we can take the number of river ties per sets of river, which is 7. So we can place 1, 2, 3, 4, 5, 6, and 7. We can add one extra here, and even we can add one extra 1, 2, 3, 4, 5, 6, 7 here, and 1, 2, 3, 4, 5, 6, 7 here. So This is the punching shear reinforcement detail using orthogonal arrangement in river ties for edge column, and for corner column just we can place 1 2 3, we can place 7 river ties per sets, and here in this direction and in this direction, because the column is a corner column. So the number of river sets will be reduced. So the number of river sets for corner column will be reduced. That is 1 2 3 4 5 6, and in this case it is 9, and in this case it is 12. So basically our slab here, our flow will have three types of columns. The first one is the corner column, the edge column, and the interior column. And we may have a column which will be located closer to the edges of the slab. In this case, we need to place our reinforcement bar ties on for direction. That is here in this direction and in this direction. So the number of the sets of river will be located just like this, up to the edges of the column here. So here just we can place just like this, So so we need to extend our punching shear reinforcement up to the edges of the column. So for the corner column, we can put just like this here, and we can put just like this here. And for this, we can put just like this here. And for this, we can put just like this. For interior, we can put just like this. Okay. This is the arrangements of punching reinforcement using orthogonal arrangements. Okay, now here there is some correction here because previously I said that from the distance from the face of the column to the effective outer perimeter is 1050 millimeter. But just there is some correction here, because here the distance can be calculated based on the the outer effective perimeter of the shear zone, meaning that we need to calculate a route starting from this point to the face of the column. So a route can be calculated, which is a route which is equal to simply a route which is equal to u out divided by 2 pi. So a route simply equals to 960 millimeter. So the distance between this point up to this point becomes what? How much? It is 960 millimeter. So the location of the last river will be at 1.5 d from u out, meaning the distance between this point up to this point, which is the distance between the last river ties to the outer effective perimeter, is equal to 260. But this distance, that means 260 millimeter, is less than what? It is 320 millimeter, meaning 260 millimeter must be less than 1.5 d, where d is the effective depth of the flat slab. So using all this information, just we can plate the last river ties here, which is 260 millimeter from the outer effective perimeter of the shear zone, and when we come to here also 260 from the outer effective perimeter of the shear zone, and in this direction also here 100. Simply we can edit this one. It is 260. So it is 260 millimeter from the face of the outer effective perimeter. And here we can simply plate the first river ties also. It is 1.5 d. I mean from 0.3 d up to 0.5. D distance from the face of the column. So how much it comes? It is around between 63 to 106 millimeter. So we have provided 100 millimeter because 100 millimeter is in between of just two values. So considering 100 millimeter here, the first stirrup location here. So 100 plus 100 plus 100. How many such kind of spacings are there? 1, 2, 3, 4, 5, 6, 7. So how much it is? It is 700. So 700 is the distance between this and what? This. This is 700. This 700. So 700 plus 260. 260, how much is it? It is 960. So 960, which is equal to around. This is when we arrange river ties orthogonally for the interior column. For the edge column, just we can replicate this into this, except excluding this wing. And in the case of the corner column, simply we can use the corner, the two orthogonal river sets, this one and this one, or this one and this one, because here we are using the corner column. So when we see also the cross section here, just simply the distance between the river ties and the first river ties interface of the colonies, it is 100. How much? It is 100. Here, this one. This distance is, it is 100 mm. Modify, except for this one. So we can make this one, it is 100. And in this case, it is 100 also. And this distance is 260 mm. So the distance between the outer effective perimeter to that of the face of the column is 960. We have already said before. And here it is 260 from this and 260 from here. And now the distance is from the center of the column is, it is 1.4 meter from the center of the column, 1.4 meter. So we can use this much amount of span for as the boundary of the shear. And this one is merely we can just correct this one. It is what? How much is it? It is 100. And this one is also, that is 100. Because the distance between the first stirrup and face of the column is, it is between 0.3d and 0.5 d. So we can prepare just like this. And when we take the cross section, we have 3 legs of stirrup. Because when we see the plan here, we have 3 sets of river here. So when we cut it, we can see 3 river at the top and 3 river at the top in order to tie the river ties here. So we are using 3 legs of stirrup. Here one full of 1 two-legged and 1 single-legged. Totally 3 legged of stirrup can be used at any sections. So just this is we can replicate this to the edge column and to the corner column, as I have already said before, by deducting the unnecessary wings. In the case of radial arrangements, we can just like this radial. We have to place the river status radial, like this, just like this. So the distance between the tangential and radial reinforcements stirrups must be within the recommended value specified in the code. Okay, now let me design for radial arrangements of revertise. Okay, to do this, I need to unlock the model. So I need to select all the column. So go to here and now override the punching machine. So here, the values for start rate, and I can use for revertise in what in radial arrangements. Now click OK. So run the analysis. So the number of reverses and revertise in radial pattern arrangement will be provided. So go to the display menu here. Just display the punching machine design, just like the 1010, which is similar to the start rail. So start rail radial arrangements and revertise radial arrangements provided the same value here, as you see, that is 1010. So just to go to the AutoCAD in order to draw the detail here. So the number of revertise facets will be what? This 7. Originally here, before that, okay, here. So we need to, sorry, here we have a column here, and we need to place 10 revertise in radial arrangement. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just like this. We can put just like this. So how many revertise per perimeter be required? 10. First one is here. Just like this. We can put just like this. Like this. So the first revertise must be just like this. So the first revertise must be placed at how many distance from the face of the column? 0.3 d up to 0.5 d. This is the effective depth. And this is the first parameter. This one. And we need to place also the second parameter. Just like this. And we need to place the third parameter until we arrive at outer parameter. This one is the outer parameter. So how can you calculate this outer parameter? The outer parameter, that is u out, can be obtained from what? From CSI SAFE. U out. If we get the value of u out, r out can be calculated. If r out is obtained, then the distance between the last revertise and this point will be the distance between the last revertise and u out can be calculated easily. How much is it? It is what? It is less than 1.5 times d, where d is the effective depth. So we need to place our reinforcement bar up to what? Up to this point. Up to this point. So the distance between this point and the face of the column, which is r, which is equal to what? R out minus 1.5 times t. That is this distance. So R out can be obtained from CSI SAFE. Just go to here, right click here. So here, this is the effective punching parameter, that is 6025. So the effective punching parameter for radial arrangement and for orthogonal arrangements are the same. So that is 6025. Sorry. Okay. So just we can place. Sorry. Here we have ten number of sets of river. Just I can put here one, 2, 3, 4, 5, 6, 7, 8, 9, 10. So uh, this is u out, and this is the basic parameter. Yeah, this is the basic parameter, and this is the location of the last parameter. This is the location of the last shear reinforcement bar. So the distance between, here we have a column. So the distance between this and this is 2d. The distance between this and this is around minus 1.5 d, and the distance between this and this is around. So around can be obtained from, that is around is a function of what? U out. U out, which is equal to 2 pi around. So around is around, which is this distance, which is around equals to U out divided by 2 pi. We can calculate just like this. Okay, so I have already calculated it. And the other point that we need to take into our consideration is the distance between this reinforcement bar and this reinforcement bar, that is located between the basic parameter and the outer parameter, should not be greater than 2d. This one. It must be what? Less than 2d. Where d the effective depth of the slab. So if it is greater than 2d, so we need to provide what? Secondary shear reinforcement set here. So we need to provide rebar ties here, just like this. So around the perimeter. So just like this, as the distance between the rebar ties, the distance between two consecutive rebar ties that is located within the outer parameter and out of the basic parameter exceeds 2d. So in that case, we need to provide what? Uh, uh, an extra or an additional secondary reinforcement set here. So in our case, the distance is greater than 2d. So just I have already provided an additional extra rebar sets here. Just like this. So here how many rebar sets are required? So it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. So total how many? 80. So 80 sets are required. So the distance between two consecutive radial here, the distance between two consecutive rebar shear reinforcement bars are less than 2d out of the basic parameter and less than 1.5d within the basic parameter. So we can check it. Dimension linear is this distance. This distance, that is the tangential the tangential distance dimension aligned this distance. That is 234. That is within the basic parameter. This is the basic parameter. So here 234 must be less than 1.5 d. Here 1.5 d is how much? 320. But in this case, how much is it? It is 234. So it is okay. And when we come to this, the last one, dimension, aligned here. So we need to check this one also. That is 312, which is less than the maximum spacing which is provided by the code. That is this distance, that is 312 is less than 1.5 t. And out of the basic parameter, here we can check this one. This out of the basic parameter and with the outer parameter, the distance between two consecutive shear reinforcement bar should not be greater than 2d. But in this case, let's check it. Dimension aligned. Just that is 466. Here 466 basically 466 2d. Where is 2d? This is 1.5d. Well, this is nothing but 230 multiplied with 20. Take as it is, because if we increase an extra river status here, so it will be more crowded. So with a reasonable engineering judgment, so we can take as it is. So this arrangement, this radial arrangement is as per the code provision which is provided by the Ethiopian Building Code of Standard and the Ethiopian Building Code of Standard, and this is for the interior column using radial arrangements of river ties. So in the case of spandrel, the principles are the same. Here the principles are the same, and what is differs only the shapes of the shear reinforcement. And for the edge column, just we can use this arrangement. This is for edge column here, and for corner column also, just we can take this portion. For this portion, we can take this portion, this one, this portion, the above or the lower one. And here there is also some correction on the value of routes and the distance between the face of the column and the first river ties here. As I have already said in a orthogonal arrangements of river ties, the same principle will be applied for the radial arrangements of the river ties. And when we come to also the radial arrangements of the river ties, so we have already corrected this one, because previously we have just here this must be corrected, because the same calculations are applied here. It is 960 mm. It is 960 mm. So the distance between the outer effective perimeter to the face of the column is, it is 960 millimeter. How it comes? Just we have already said the u out divided by 2 pi. So it provides 960 millimeter. This is the radius of the around. That is the outer effective circumference or circle will have a diameter of 960 millimeter with reference to the face of the column. So here previously I have written this one as 150 millimeter, but 150 millimeter is not in between of 64 millimeter and 106 millimeter, because this distance, the first straps must be located between 0.3d up to 0.5d from the face of the column. So when we take this value, so the value must be less than 106. So 100 must be taken as the distance between the first strap and the face of the column. So keeping this 100 and all the rest spacings are 100. So how much distance will have between the face of the column and the last straps here? This distance become it is 960. So 960 mm. And when we come to also the location of the last stirrups and the outer effective perimeter, it is 260. How it comes? So this distance must be less than 1.5 d. So 1.5 d is it is 320. So 260 is less than 320. So our location of the last stirrups is as per the provision of the code, which is specified in Eurocode and Ethiopian building code of standard. And just this so all just at the very of the outer effective perimeter and the last location of the rebar ties is similar. That is 260 here, 260 here, and 260 here. That is 260 here. So this is the proper arrangement of the rebar ties when we arrange it in radial pattern. So when we come to the section, just it looks like this one. Here the last rebar ties is located 260 millimeter from the outer perimeter here, and the distance between the first straps and the face of the column is it is millimeter here. Yes, we can uh, arrange it just like this. It is 960, which is the distance between the faces of the outer perimeter and the face of the column is 960, because 960 is it is the size of our route, and here it is our routes. So this is the proper arrangements of river ties when we arrange it in radial pattern and in orthogonal pattern. Okay, now let me show you the second option that we have to use for the design of punching. That is, using drop structure. So now let me select this one, and here now let me override the punching check. Then here I need to make this no, because I'm not going to use the revertise and start rail method, and I need to use a drop structure. Now click OK. Yes. So here first I need to define the drop structure that I'm going to use at a specified points where there is a shear failure. So to do this, go to the define menu here, and go to the section and the slab section here. So I have already just defined the drop here. In order to save time, just unlock the and you go to the define menu and the slab section. Here I have already defined. If you wanted to add a new section here, then here drop to. Just you can make drop to here, and here you can make the section that is 400, and you can select the drop here, and you can click OK. Or for just to save time, I have already I have already defined drop 400. So just I can check it, that is 400, and this one is make it 500. And here the concrete is selected here, and the thickness is 500, and the type of the slab is it is drop. So click OK. And so just go to here, and I need to specify the here just select drop 500, and you can make just this one that is 400 first. I mean 4000 and 4000, and just click this one, and now select this one, Sorry, now run the analysis. So here I am I am designing this column for punching using a drop structure. So we need to apply drop for the rest of columns. So go to the display menu here, show punching sheet design. Here, previously this ratio it is around 1.1, but now it reduces. That is 0.9 because I am just providing a drop under the column here. So in similar manner, just I can select this one. Just select this one and edit. Okay, before and select this one, edit. So replicate it and pick this point and apply this. That is apply. So we can just put the drop structure under the column which are failing in punching, just like this. Okay. Now run the model. Okay, display punching issue. Just we can see you can see the ratio is reduced from 1 point something value to the value which is less than 1. That is this one is 0 0.6, 0 0.7, 0 0.9, 0 0.5, 0 0.6, 0 0.6, 0 0.6, and 0 0.7. And a very nice result 0 0.6, 0 0.7, 0 0.6, 0 0.7, just like 0 0.5. And this one was previously that 0.9, it was working. So here we can just design punching using drops. And the other is just by increasing the slabs. Okay, now let me show you. Increasing the thickness of the whole slab is not, advisable because it is too costly as we will be increasing the thickness for the whole slab. So in order, for the sake of clarity, now let me show you how it comes. So, select the drops slab section. Go to the edit menu. Now delete it. So now select the whole slab. So before that, now go to the slab section here. So the flat slab, add copy of this one. Now slab for punching. That is, we can make it is, 300. So select this one, make 300. Okay, okay. Go to the select menu here. So go to here. That is, select the floor. Then now assign the shapes with override the slab section. Slab section for punching, apply. Okay, now run the analysis. So just we can see how The punching shear ratio decreases when we are increasing the thickness of the whole slab. Just the aim is just to show the relationship between thickness and punching. Then just go to the display menu. Then just design for punching that it display the punching shear here. It is a very nice result also. Here we are getting a very nice result. That is, using a thickness of 300 millimeter flat slab, will avoid the failure of punching. That is 0.7, 0.8, 0.9, and here 0.8, 0.8, 0.9, 1 point here. So we need to just accept with engineering judgment at this ratio because it is nearly 1. And this is also nearly 1. Just we can accept this one and we can tolerate it. And this is 0.9, 0.8, 0.8, and 0.8, and 0.8, and 0.8. So just we can apply a drop structure having a thickness of 500 with the length width value of 4 meter, or at every places where there is a punching shear failure, or we can increase the thickness of the slab from 250 to 300 millimeter, or the other option is just keeping the thickness of the flat slab 250, and we can apply the shear reinforcements at the place where there is a shear punching failure. So this is all about for today's tutorial, which is the design of punching using rebar ties and stud rail in radial and orthogonal arrangement pattern using the Ethiopian Building Code of Standard and the European Building Code of Standard with the support of CSI SAFE theory. So if you are interested in my videos, just try to share all my videos to your friends so that your friends will be getting more relevant tutorials that have been already prepared with references to the designing of this story building and even steel structures. And also, don't forget providing me comments and questions so that I will be answering your questions and your comments within a short period of time. So don't also forget pressing the bell icon because you will be receiving more updated tutorials within a short period of time. So this is all about for today's tutorial, which is tutorial part 27, which have been already focusing on the design of punching in flat slab using CSI SAFE 2020 as per the Ethiopian and the European Building Code of Standard. So next time we will discussing about the foundation part. So that will be a very interesting topic. So see you next time. Bye bye.